Hi students, welcome back to Wisdom Academy YouTube channel. In the previous video, you have learnt about dispersion of light and atmospheric refraction. In today's class, you are going to learn about scattering of light and Tyndall effect. Tyndall effect is, the name is given after the scientist John Tyndall, who did lot of researches to talk about that. At the end of the class, you will know what is this effect. For that, I'll take one small experiment. So what I'll do, I'll take one jar, or I'll say I'll take one beaker. In that I will fill water and I will use a laser light here. This experiment is very simple and even you can try it home. So what I will do, I will just take a jar and fill, this is a transparent jar, glass jar, fill it with water, and I will use a laser light, and here there is some wall. I will see the projection of this laser. I can see at this point there is some projection of laser. Then I will try to observe what I can see inside this jar. What I will find that I cannot trace any light inside the jar, rather I can just see the light coming from here and the light is falling here and filling the image, making the image here. So it will be like dark red spot. Now what I will do, in this water I will add milk. The moment I add milk and mix it nicely, then what I will feel? I will feel that this path of light which is traveling inside this started becoming visible. So what I saw, that when I added the milk inside the water, the path of light which was untraced in the previous case is able to see now, is able to be seen now. So why does this happen? This happens due to the principle of scattering. I will tell you what is scattering of light. Till now what you have learned in reflection of light, you have learned that whenever a light ray is coming and hitting a surface, it reflects back in one specific path. But now I am going to contradict this and I want to say that that is valid only if the surface is a big surface. Suppose I take a small particle. If I take a small particle and on this particle if the light ray is coming and hitting, then instead of going back in one direction, it will be going in the multiple direction. So what you learned by this? You learned that whenever a light ray is hitting a very small particle, you can ask yourself, how much small? In the range of nanometers. In the range of nanometers. So when particles of nanometer size are hit by the light will not reflect back in one direction, rather it will scatter in all the directions. So what happens when we put the milk inside this solution, inside this water, and made a solution of this, and when I pass the light ray from it, I could trace that each particle, suppose one particle is here, one particle is here, one particle is here. We know that all particles will be very nearby to each other. All these particles are scattering the light in all the directions. So whether you are seeing from here, or whether you are seeing from here, or whether you are seeing from here, from all the directions this light is coming. So you are able to trace the path from anywhere where you see. So this particle which scatters the light is known as colloid particle. It is known as colloid particle, or we say colloidal solution. So colloid is the particle which scatters the light. Now you can ask me, what is the range of this colloid particle? The range of colloid particle is from 1 nanometer to 1000 nanometer. So all the particles which are coming in this range, 1 nanometer to 1000 nanometer, are known as colloid particles, and whenever the light ray is hitting these colloid particles, they will be scattering in all the directions. Now if the size of the particle is less than 1 mm, is less than 1 nanometer, sorry, the size of a particle is less than 1 nanometer, then that particular thing is called as solution. And since the size is too less, it will not scatter that much. Scattering will be there, but it will be very, very feeble and you will not be able to see that. It will be very, very less. That is the reason we cannot view it. So scattering is best in the colloid particles. What if the size is more than 1000 nanometer? If the size is more than 1000 nanometer, that kind of particles are called as suspension. So if size of particle is more than 1000 nanometer, suspension. Will the suspension particles Scatter light, yeah, they will scatter, but when there is a problem in this kind of suspension particles, the problem is that it's being heavy, being more in size and being heavy, they will settle down easily. So in water, if I add some suspension particles, initially I will be able to see some scattering, but the moment scattering starts happening, it will fall down. So the particles which is coming here, since it is a big particle, it will not remain here, it will fall down, and due to gravity it will come down. So again the path remains untraced. So today by this thing, what you can understand? You can understand that scattering is best seen by the colloid particles, and why it happens? Whenever a light ray is coming and hitting this colloid particle, it gets scattered in all the directions. Once again I want to say that size of the colloid particle is in the range of 1 nanometer to 1000 nanometer. If the particle size is more than 1000 nanometer, scattering will happen, but it will not be seen for a longer time due to the gravity effect. This particles will settle down, and if the size is less than 1 nanometer, that is if it is a solution particle, then once again the scattering will be very minute and very feeble, that you will not be able to see it. Fine. This effect is called as scattering of light, and this was found first by John Tyndall. John Tyndall did a lot of research in this, and how this came to his mind, you can see in the forest regions, you can see there is light coming, and in the forest, if there are lot of tall trees are there, then you can see light is coming and getting scattered. You can very clearly trace the path of the light. So why it happens? Because of the presence of colloid particles. So these colloid particles scatter the light, and when it comes to your eyes, it looks that the path of light is visible to you. This is known as scattering of light and Tyndall effect. Now we are going to see why sky looks blue. Have you ever thought why sky looks blue? Because I have only told you that light comprises of 7 different colors, but it is a white light. So light which is white in color, when it comes from sun, why it looks blue? So have you ever felt this? Because we are on the earth. So suppose you are standing here and there is a sun. When it reaches you, it should be white in color. But how it looks? Does it look white? No. It looks blue in color. So when you see the sky, it looks bluish to you in color. Not only that, sun, what color it looks? Sun, it looks yellowish in color. Though it is white, it looks yellowish in color. And some people will say, sir, I have even seen sky in red color or orange color during sunrise and sunset. So all these answers of color, today I am going to give you. Why sky looks blue, why sunrise, sunset looks yellow or orangish red, and why sun looks yellow. So all these answers I am going to give you today. I will speak one by one. First I will tell you about this white light. Since I told you in the topic of dispersion itself that white light is made up of 7 different colors. That is Vibgyor: violet, indigo, blue, green, yellow, orange and red. And I remember when talking about dispersion of light, I also spoke that wavelength of each light is different. Wavelength of every color is different. Wavelength of violet is minimum, it is shortest, and wavelength of red is maximum, it is longest. Now, though it is little high level for you, but I am going to tell you now, just keep in your mind that you will learn in 12th standard that light, though you have studied as a ray, it also behaves as a wave, which you will study in your higher classes. That light, though we as of now we are studying it as a ray, it is also a wave. So when light behaves as a wave, violet light will have short wavelength, so it will be more compressed like this, whereas red light, which has high wavelength, will be more free like this. So this can be, just for example I am saying, this can be a red light wavelength and this will be the wavelength of a violet light. Fine. Now our atmosphere, Earth's atmosphere, comprises of a lot of gases, like we have helium, we have hydrogen, we have oxygen. So all these gas particles are very small in size. Being very small particles, what it does, it starts scattering light only of lesser wavelengths. So size of the atmospheric particles will be near to violet size. So what happens? Violet's wavelength. So what the small particles will do? It will start scattering violet light to you. So in this Vibgyor light, this light starts getting scattered more. So when it starts getting scattered, what comes to your eyes should be violet, right? Then why it is blue? I am itself saying that violet light has a shortest wavelength, then it gets scattered, then why what we are seeing is blue? I will tell you the reason for that. The reason for that is, out of white light, these 7 different colors are not in equal composition. The percentage of violet, percentage of red is not same. It varies. And I'll tell you, this violet and indigo colors are very less in composition. So white light, the percentage of violet and indigo is very less. Moreover, it starts scattering. So first it will start scattering violet, and then it will start scattering little bit indigo, and finally when all these things are scattered, bluish scattering start happening, and what reaches to your eyes is almost blue in color. That's why wherever you see, it is blue. Now if I can ask you one question, what if the atmosphere is not there? Will the sky look still blue? No, it will not look blue, because now you understood that sky looks blue is only because of the atmosphere of the earth. That is the reason if you are on moon, then the sky will not look blue to you, it will look blackish. You can see and go any photo of the people, like when we went to moon, astronauts, if you see the photo of that, you can feel that everything looks black outside. So why that happens? Because moon is has a surface where there is almost no atmosphere. So being no atmosphere planet or body, celestial body, it scatters almost no light, and that's why everything looks black around you, but not in the case of earth. On earth, since we have an atmosphere, so the scattering of light makes our sky to look blue in color. Now let us see why sunrise and sunset is red in color. So sun looks reddish when we are seeing some sunset or when we are seeing sunrise, but the sun, does it look same reddish when we are seeing it in the afternoon? No, right? Why is it so? Today we are going to learn about that. What happens whenever the sun is above, like it is an afternoon time or morning time? What happens? Suppose you are on the earth and sun is right above you. So when the sunlight is entering to you, it passes the atmosphere. I told you already, this is the atmosphere, and the sun ray passes through the atmosphere and comes to your eyes. I told you, while passing through atmosphere, the scattering of light starts happening. Violet, indigo, blue scatters maximum, and you are able to see bluish everywhere. After that, green scattering happens, and then what reaches your eye remains only yellow in color. I hope you are understanding what I am trying to say. When the light ray is traveling from the sun to your eyes, the most constituent of the light, like violet, indigo, blue, green, these things get scattered, and when it reaches your eyes, only yellow reaches your eyes. That's the reason you can see the sun to be yellowish in color. Then why it looks red during sunset, sunrise, sunset? See, you can understand that whenever there is sunrise or sunset, we are seeing the sun at the horizon, right? So horizon means, suppose you are here, then you are seeing somewhere here. So this is the horizon, and here the sun is settling down. So when the sun comes in the horizon position, it is one of the longest distance the sun is present. Moreover, the light ray has to travel more in the atmosphere itself. Suppose this is the atmosphere level, then when the sun was at this position, then it will cover only, suppose this is, I will just draw it once again. Yeah, let this be the atmosphere, and this is the earth. So sun, when it is present above, then it travels like this and very little distance in atmosphere. When it comes in the horizon position, most of the sun ray, when it is reaching to you, it is coming in the atmospheric region only. So scattering keeps on happening. Scatters violet, indigo, blue, green, yellow. Even yellow starts getting scattered. So what reaches your eye will be comprising of orange and red color. That is the reason when you see the sun during sunrise or during sunset, it looks reddish in color. I hope you would have got some clarity. So everything is linked with scattering of light. So scattering of light, I told you, particles which are very, very small, they will start scattering the light. So smaller particle size is much smaller than even like violet's range, wavelength of violet range. So what happens? It starts scattering violet indigo light. So violet indigo is scattered more, that's why everything looks bluish in color. Violet indigo blue, I mean to say. And when the sunlight enters to you, most light gets scattered, yellowish reaches your eyes. When it is going in the horizon position, even yellowish gets scattered, orange and red reaches your eye, and that's why the sun looks reddish in color. For proving this, you can even do the same experiment what I did that day. What you can do, you can take a jar, fill this jar with water. Now what you do, you place, suppose I am going to do make a 3D diagram for you, that will be easy for me to understand. I am going to place the torchlight, white torchlight, somewhere here on this position, and I am going to see from this side how it looks. in this solution I have added milk. So I made some colloid. Why have I added milk in the water? To make some scattering to happen. What you will observe, when you see this white light coming on that side, no, it look yellowish in color. But same torch, if you use from this side, it look little orangish color. You can try this at your home even. Why it happens, you know? Because in this case, the light is traveling very less distance, where here the light is traveling more distance. Traveling more distance, the scattering of light is more of all these wavelengths, and what reaches will be orange and red in color. So this is the reason why the sunrise and sunset looks red, why sun looks yellow, why the sky looks blue. Some students are getting doubt that why do clouds look white then? When you are saying sky looks blue, the clouds should also scatter the light and it should look blue. Why it looks white? The reason is the cloud is made up of water particles, and water particles are bigger in size. So being bigger in size, all the white light, nothing is it is able to scatter. So all the white light comes to your eyes. That's why it looks white in color. So with this, I am going to end this video, and with the end of this video, I am ending the second chapter of physics itself, human eye in colorful world. In this chapter, we have learnt about eye, we have learned about parts of eye, we have learnt about defects of eye. Then I have talked about how to correct that errors what you have in your eye. Then we have learnt about dispersion of light through a prism. We have learnt about atmospheric refraction. Today we have learnt about scattering of light. We also learned some good facts about some Tyndall effect. Then we learnt about why the sunrise and sunset is red in color. We learnt why sky is blue. So please like the video, share with your friends and subscribe our channel. Thank you.